All right, here are the notes for 6.3b. We're continuing to talk about binomial random variables, and specifically, what does the distribution look like? And you saw one of those in the warm-up, and we'll just continue what we were doing there. So, shape, center, spread. That's where we're headed. Shouldn't surprise you, actually. So the one you saw in the warm-up was skewed right, but they're not always skewed right. The reason the one in the warm-up was skewed right is because P was less than Q. It was less likely to get a success and more likely to get a failure, or another way of saying that is that P was less than 0.5, less than half of a chance of getting a success. And so what that does is it makes your distribution lean towards 0. You're more likely to get 0 than 1 because 0.5 is in the middle, and that means most of the data is in this region, and that would be skewed right. However, it might be logical to you, and it might not, that it could go the other way. It might be sometimes our successes are all over here, more likely to happen. So if P happens to be bigger than 0.5, then it would be skewed left. And just think about where the data would land, right? Less than 0.5 is most of the time you're over here. More than 0.5, most of the time you're over here. If it's equal to 0.5, it's symmetric. Not normal, but it is symmetric. In fact, it's symmetric and mound-shaped, but that mound might be different depending on how many possible outcomes there are and how many different possible outcomes is a good enough word for it. All right, so that's the shape, kind of logical, common sense. Center. Okay, so the center, we also worked with this in the warm-up. There were 6 different possible outcomes, and they each had a 1/4 chance, and so we ended up doing something like that, 6 times 1/4, which was 6/4 or 3/2. Or that's the average that you would expect to get, the expected value. So the expected value, which is also the mean, is basically, this came from the number of trials, and this came from the probability of success. It's basically n times p. That's the official formula. It's an easy formula, isn't it? Just take n times p. And it's the reason that was in the warm-up is it's kind of a common sense thing that I hope makes sense to you, that you would take the number of trials times the probability of success. And that's what you expect to have happen. So also not too bad. And then spread. This formula you probably couldn't guess, so I'm not going to make you try and guess it. I'm just going to say standard deviation is officially the square root of n times p times 1 minus p. That's the way the book writes it. I like to replace 1 minus p with q. And again, if I forget to say that, somebody will ask me, what's q? It's 1 minus p. So anyway, NPQ, I have it memorized that way because it's easy to memorize. But you don't have to memorize it. You're going to write it on a formula sheet and use it. Your weekly summary, that's what it's for. In the warm-up example, we had 6 was n, and the 1/4 was the probability of success, and the probability of failure was 3/4. And so then you square root all of that, right? So if you multiply this all out, you get 1.125, and then when you square root it, you get 1.06, which is the typical deviation from the mean for the quiz that we were talking about in the warm-up. All right, so a couple new formulas. This is kind of a common sense thing, but you do need to know it. You need to be able to figure it out. Mean and standard deviation. I should probably put a box around this one also, because those are the formulas we're learning today. So let's do one more example of that sort of thing, and then I have two more things to tell you after the example. Type O blood. If you've ever donated blood, and especially if you have type O, you are a very popular person. Type O blood is very valuable because type O blood can be put in anybody, and they won't react to it or their body won't reject it. So type O is like the universal blood donor. And it's about 25% of the population that actually has type O. And the other 75% have other types of blood, and so they're not quite as valuable, but they're still useful. So that's the probability of success and the probability of failure in this case. Let's say we're going to take 5 samples of blood. In fact, let's say we're working in a blood bank and we're trying to find a sample of blood that is type O. I want to know how many type O's I'm likely to get if I look at 5 samples. So this is my number of trials. And so we're talking about many, many samples of size 5. Picture that. And I want to know the average number out of those 5 that have type O. And notice I'm not finding a probability, so I'm not using yesterday's formula. I'm using, or not yesterday, but the previous lesson's formula. I'm using these to find the mean and the standard deviation of this distribution. So just practice with the formulas. Mu of x, well, it's n times p. N is 5. P is 0.25 or 1/4. And so that's 5 times 1/4, which is 1.25. And that is my average number. Now remember, an average does not get rounded. You might say to yourself, well, I can't get 1 1/4 samples, but I'm not talking about on a specific time that I chose 5. I'm talking the average of many, many times that I chose 5. And this is a perfectly good average. On average, 1 1/4 times out of 5, I would get type O. And then standard deviation of that. I could do that calculation also. It's the square root of NPQ. So it's the square root of 5 times 0.25 times 0.75. I like that the calculations are not that hard this time, right? I mean, no problem. Well, I hope that's no problem. Anyway, I should put it down here so it fits better. I got square root of 0.9375, and that comes out to 0.968. So in other words, in samples of size 5, I would get an average of 1.25 type O's in that sample, and it would vary above and below that by about 1, about a little less than 1. So it could go anywhere from none to about 2.25 or so, and probably not very often would I get more than that. So that is an example of using those formulas. If we were in class, I would ask you if you had questions before we go on. I want to show you some shortcuts for what we did in 6.3a. So a couple of calculator shortcuts that were not in those notes, but I thought I should put them somewhere. So you already know that the probability of x being a certain number, which we're going to call it k is the number of successes out of n trials, successes out of n trials. You already know this formula from the last lesson, and it looks like this: p to the k and q to the n minus k. And we did some practicing of that in the warm-up, and hopefully you're getting better and better at that formula. But there's a shorter way to type it, so you are also allowed to type it this way. So today's the day I'm going to tell you there is a shortcut called Binomial PDF. If you'd like to know, PDF stands for Probability Distribution Function, and it basically finds the probability that x equals k given that we know p and we know n and we know k and all that. In fact, those are the 3 things you need. You need n and p and k. So the number of trials, probability of success, number of successes. And if you're wondering where to find that command, this Binomial PDF thing is in second vars. It's the same place you would go for a normal CDF. We'll talk about CDF in just a moment. But I could do, in fact, let's do this last example from lesson 6.3a. Again, in this case, n is 5, k is 3, and p is 1/6. So I could also do second vars, normal, not normal, further down, I think it's towards the bottom actually, Binomial PDF, not CDF, because I'll tell you that next. PDF, number of trials is 5, probability of success was 1/6, and the x value, that's k, is think it was 3. If I'm wrong, I'll fix it in a minute. So it was 3. Very good. So what it does is it puts them all in the parentheses like that and enter. And cool, it's the same answer we got before. Before I tell you what a CDF is, I want to say if you are taking the AP test and you type this as showing your work, it doesn't count as showing work unless you label these 3 things with what they mean. So you would have to either label it as n equals 5 or label it as 5 trials. You have to label these numbers to prove you know what they are, or else they won't count it as showing work, which is kind of picky. They do count this as showing work even if you don't label the numbers. So it's like, I think it's based on the fact that some of the people who grade the AP exam are college professors, and they may or may not allow this in their class. And so this counts as showing work. This does not, unless if you label them all, then it's okay. So I would just say show work very thoroughly on the AP test instead of just typing this. But you could show this and then type this, and that would be fine. So then somebody always asks me most years, what in the world is CDF then if this is PDF? CDF is the cumulative distribution function, which is x is less than or equal to k. So that's like the probability of 0 plus the probability of 1 plus the probability of 2 plus all the way up to k, and so much faster to do binom CDF. And again, you'd have to put NP and K in there. And that would give you the probability of getting that many or less. And then if you want to do something more complicated, like the probability of x is greater than, let's just pick a number like 4, you have to do a 1 minus in that case. And because this is discrete, you can't have 4.5 or 3.5 or anything like that. This is 1 minus the probability that x is less than or equals to 3. You'd have to change that. 4 or more is the opposite of 3 or less when you're talking about discrete. And that's tricky. And so I'm telling you about it now just in case you need that. It's still NPK with commas. All right, but so the calculator can do that, or you could just add up the probability of 0 and 1 and 2 and 3, and that's the same as, 4 and 5 and 6 and however many you have. So I wanted to give you those shortcuts because they will make some of your homework way easier. And then I have one more thing to talk about. So try to keep this from being too terrible. So I talked up here about how sometimes it's symmetric. If p is 0.5, it's symmetric. Or if it's not 0.5, it's not symmetric. This symmetric thing might not be perfect. Like it might be something like this, or it might have more bars to it, but because it's discrete, it's definitely not a normal curve because it's just, it's jagged. It's like stair steps instead of a normal curve. But if p is big enough, no, not if p is big enough. If n is big enough, that smooths out the curve and you get close to normal. So let's talk about that. Big enough n, that remember n is the number of trials, how many die rolls you're going to do or how many samples you're going to take. What that does is it smooths out the curve and makes it more and more closer to a continuous curve instead of discrete. And if n is big enough, you get close to a normal curve. And so if this happens, you can use a thing called the normal approximation. Now that was a lot more useful back in the olden days when they had the table A, but they didn't have the binom CDF on the calculator. So you really could just do binom CDF all the time. But the normal approximation was invented partly because it's a shortcut to keep you from having to do this. So let's do an example of that. Actually, first let's talk about how big is big enough. Big enough, this works if n times p is greater than or equal to 10 and n times q is greater than or equal to 10. So let's think about this. N times p, what is that? That's the number of trials times the probability of success, which is the average number of successes, or you just say number of successes. If the number of successes in your however many trials you have is bigger than 10, and the number of failures is also bigger than 10, then you can use the normal approximation. So let's talk about that. I'm going to do it more than one way, just to show you that it is a reasonably good approximation. But let's say we're back to random sampling again, and we take a random sample of 2,500 adults. That's big. And let's say we ask them a question, and I don't even care what question it is. I'm just going to say, let's say P is 60% chance of them saying yes to my question, whatever it is. So that's my probability of success. So now, if I want to know the probability of getting out of this 2,500, I want to know the probability of getting 15, 20, or more yeses. So I'm going to tell you the hard way and the easy way to do this. Actually, they're both not too terrible with a calculator, but so that's the probability that x is greater than or equal to 1520 out of 2,500. That is what we want to find. So now if I didn't have the shortcuts, I would be finding the probability that it equals 1520 with one of these, right? Plus the probability that it equals 1521, plus the probability that it equals 1522. Do you get the idea? I already am tired after only 3 of those, and I would have to go all the way up to 2,500, unless it was shorter to go 1519 down, but it wouldn't be because there's still way too many of this thing being added together, which is why they invented the normal approximation, by the way. I'm going to do it both ways. I'm going to do the normal approximation first, and then I'm going to do the binomial CDF method, and we'll compare them and see how they go. So since the sample is so big, n times p is pretty huge. It's 2,500 times 0.6. That's how many yeses we expect in our sample. Times 0.6 is 1,500. Oh, good, that's bigger than 10. Of course it is. N times q, that's 2,500 times the complement of p. Remember, q is 1 minus p. I have to say that every day for a little while at least. 1 minus 0.6 is 0.4. And when you do that, you get 1,000. That's also bigger than 10. So this means I can assume that this distribution is approximately normal. Doesn't mean it's perfect, means it's close enough to get a good approximation. So I could do this with a z-score. I could do this by finding a z of my 1520 minus my mean, which by the way, I just found the mean. That NP thing was the mean. 1,500 is how many I expect to have happen. Divided by, I would need to find my standard deviation. So this thing right here ended up down here because that's mu x. I would need to also find my standard deviation of x, which is square root of NPQ. And when you calculate that, you get about 24.5. And use that to find your z-score. Okay, so if you do all of that, you get a z-score of about 0.816. And then you could do what we've learned before with z-scores. You could do the probability that z is, we want greater than 0.816. And you could do normal CDF or look it up on the table, either way. 0.816 goes first because it's a greater than, and you get an answer. So let me just make sure that I calculated all of that right. I'm going to recalculate this to make sure that it's right because I just copied it from last year's notes, and that's not very good practice. It was square root of 600, which is 24.49. Okay, that's where I got that from. This subtracts to make 20, and if I do 20 divided by my standard deviation, I get 0.816. That's where that came from. And then second vars, normal CDF, answer I just had, and 999. Well, a few more 9s would be nice just to be sure. Doesn't matter. 0.207, about a 20% chance, 21%, something like that. Or I could do a binomial CDF method, and remember that greater than is 1, you do 1 minus the less than, so we do 1 minus the probability that x is less than or equal to, we'd have to break this, go 1 less and do 1519, that's fine. So I could do 1 minus binomial CDF, and I would put N, which is 2,500, and then P, which is 0.6, and then K, which is 1519. And this should come out close, but probably not exactly the same because it is an approximation. This is an approximation. This is the accurate answer. So second bars, binom CDF, not PDF because I want to less than or equal to CDF, and I put in 2,500 and 0.6 and 1519. And I get that is wrong. I forgot to do 1 minus. There we go. 1 minus that answer. That's better. 0.213. This is the accurate answer. This is, or more accurate, I should say. This is the approximate answer. They're close enough. And somebody basically tried this with a bunch of different numbers and decided how big this would have to be to make it work. And as you can see, it's close. It's about 21% either way. All right, so that is how you use those. That's the most common reason we would want to find the mean and the standard deviation, is so that we could do this normal approximation. And again, like so many other things in this book, this is going to come back in other chapters, and we're going to use this a lot later on. And so you're going to get really, really good at it. But this, I realize, is the first time you've seen it. So it's a little difficult at first, mostly just which formula to use when, and 2 different ways to find the probability depending on whether you want to do the super accurate way or the approximation with a normal curve way. The book's going to ask you to do the normal approximation some of the time. All right, that's enough for today.